different way of looking at it. Okay, so here's a problem. Again, shear moment, shear force and bending moment diagram. Now, you'll notice right off the bat that's a little bit different than some of the problems we've been working. In that I've got a pin and a fixed connection. So if I try to draw a free body diagram of this whole structure, I'm not going to get too far, right? I'm going to run out of equations. So I'm going to have to take it apart here. So just to get started, to get the bending moment and the shear force at A, the shear force at B, and C is going to take a little extra work. You'll also notice that the loads are triangular. So what's our shear diagram going to be?
Shear diagram is going to be
it's going to be a parabola. So we're going to have to find areas under a parabola. So that might be interesting too. So I thought this would be an interesting problem to try, or to at least examine. So let's look at the first. I'll draw a free body diagram for the first section. And I will assume, again, at A, that I have a positive shear at A. And that at B, I have positive shear at B. There's no moment at B because it's a pin. There's no moment at A because it's a pin. And then I'll go ahead and get the concentrated equivalent of this force. So I've got 1/2, it's triangle, so 1/2 base times height. That looks like 450 pounds, right? You guys buy that? And that would be 2 feet from A or 4 feet from B. Now let's look at the other side. So I'm going to assume positive shear on that side from B. And then I get over to C, I'm going to assume positive shear at C and positive bending moment, because it's a fixed connection, at C. And then I'll have another concentrated equivalent force, which will be represented by this area. So 1/2 base times height. That's what, 225? Is that right? And the distances will be, it'll be 1 and 2. Everybody see that? So let's start. So I'll call this free body diagram number 1 and free body diagram number 2. So I'm going to start with free body diagram number 1, and I should be able to solve for these very easily. I'll just sum moments about A, make sure I have equilibrium. So about A, the 450-pound force creates negative moment and has a moment arm of 2 feet. And my shear at B creates what? Positive or negative moment? Negative. Negative moment, and it has a moment arm. I left that off, but that's 6 feet. So the shear at B is equal to 150 negative? That sound right? Anybody check that?
Yes.
Also staying at free body diagram 1, I can sum my forces in the y direction, and I have shear A acting up, shear at B acting down, my 450-pound force acting down. So the shear at A is positive 300. Everybody okay with that? So let's just now take my shear at B, apply it to the other side, and find these other reactions. So now going to free body diagram number 2, I'm going to sum moments about C. The reason I'm doing that is The shear at C won't create any moment there. I'll have my unknown moment, and it'll be in terms of my shear at B, which I've already found. So looking at this free body diagram, using right-hand rule for my sign convention, the moment at C is positive. What about the way I've drawn it here? What's the moment of this shear force? It's negative, right? And has a moment arm of 3. And then the force is positive, and it has a moment arm of 1. You see that? Remember, I know the shear at B. What is the shear at B? Negative 150. So I plug in a negative 150 there. So what is the moment at C? It looks like it's going to be negative, right?
Negative 675.
Sounds reasonable. What you guys got? Yeah, 675. And that would be pound feet. And it should be negative? Yes, negative. And then I can sum forces in the y direction. Make sure I'm in equilibrium. What do I have? I have my shear at B acting up, my shear at C acting down, and my applied force also acting down. So what is the shear at C? Remember, the shear at B is negative. So the shear at C is going to be, what is that, 375? Negative? Yes? No, that should be, I did that wrong. So I put in my, this is negative 150, minus that is negative 375. That's right, negative 375. Okay, so I've got my pieces. So now let's. There's my left side and my right side for my template. I know something's going to happen here. What's going to happen here?
It's going to go to 0.
What's going to go to 0, Mr. Iffy?
Your shear.
No, my moment. Yeah. So that's going to be a good point for us. If I don't match 0 moment there, that's not going to be good for me. So let's come over here and establish a positive axis for X and Y, and all of our values will be in pounds. So let's start. What is the shear at A?
Shear at A is
300. What should be the shear at C?
Shear at C is negative 375.
Let's hope we get that along the way. So, using our relationships, that the change in shear is the area under the load curve. What is the change in shear over the first 6 feet? What's the area in the load curve, right? So that's 450. So what's 350 minus 450? Negative 150. What is the shape of that graph?
It's a parabola, and it starts concave by.
Well, remember the slope is equal to the load, right? So what's the load at the beginning?
It starts out real heavy and dips light.
It's going to start off with a big negative slope and end up with a 0 slope. So you're going to get some kind of curve that looks like that. I can tell you right now, from a geometric standpoint, that's going to be trouble.
Yeah.
Well, let's see if we can continue anyway. So what happens at B?
Just the opposite.
Is there any applied force there at B?
No.
No, but we know internally what's the shear at B.
Negative 150.
Hey, look at that. We got negative 150. Sweet. Now what? The change in shear between these points is the area of the load curve, which is negative what? $275? So 150 minus 275, or I'm sorry, 225 is 375, so it matches. What's the shape of the curve? It starts off negative 0 and it gets larger. So it curves like that. Oh my! Never seen one of those before. You like that? I do. I think that's a good one. There is a problem here. What is the problem? Well, when I want to find the change in moment as the area of the shear diagram, so let's just do this real quick. I'll establish my positive x and positive moment axes, and all my units will be pound feet. What is the moment at A? 0. What is the moment at B? 0. What is the bending moment at C?
Negative 75.
So I got 3 points on my curve already. I got no shape though. And what do I have here? That becomes a pretty interesting point. Why? Because the change in moment here is going to be positive, and then the change in moment here is going to be negative. So that area will tell you what you're going to go up to get to this moment, and then that negative area should bring you back to 0. And then whatever the area of that thing is going to bring you down to there. Right? So if you want to know the maximum positive moment, it's going to happen right there. But I don't know how to get it. Do you?
Sure you do.
Well, I don't know the area of this. This is a general segment of a parabola. There's no formula for that.
You know what calculus was for? Area under the curve.
Well, I'm glad you said that. We could easily write the equation of this line, integrate it, and get the equation of this line, and then therefore be able to integrate it anywhere we want. But that means you need to write the equations. So I wanted to show you this only as an example of where the construction of a shear force and bending moment diagram can present some troubles. And at this point, you would almost want to say, well, if I've got to go through all the trouble of writing the equations, I'll just abandon it and go back and write the equations and just have them. But this, at least quantitatively, well, I mean, we got the shear. Shear's done. But to be able to get these values, you're going to have to write these equations. So the shear force and bending moment diagram is always good to give you kind of a view. And I also know, because of the shapes of these things, that my diagram is going to look something like this, and this is going to be, let's see, negative getting, well, I didn't draw it right, but it's not going to kink there, but it's going to look something like that. I just don't know what that is yet. I have to know the area of that part of the curve, and I don't know. I can't do that in the top of my head. And I don't think you can either, unless you're like one of those guys from that movie, Simple Mind, or something like that, or Rain Man, one of those kind of guys. Any of you qualify?
Is that not a testable question?
Bingo. Yeah, so I wanted to show you this to warn you that when you see triangular loads, could really cause you some issues with the construction in the graphical technique. Writing the equations, you should still be able to write the equations.
But I got all that practice last time.
And you got lots of practice, Mr. Moore.
So if that pen was not there, would it?
You couldn't solve the problem.
You still couldn't solve it?
No. Okay. So that's kind of a a failure, but just to